Hey guys, so this is our video on statistics. So, as you may know, quantum mechanics has a lot of statistics in it. Um, it's a really big part of the theory. Um, and you may not be familiar with all of these statistics that we'll have to be using, which is why I'm having a brief introductory video on this. So, throughout the most of this video, we're going to deal with this hypothetical situation. I'm going to give an example data set. But first of all, what is a data set? A data set, and it is, I mean, pretty obviously it's a set of data, right? And so we'll have a letter, uh, some measurable variable will j, and j can equal 1, it can be 2, actually it can also, usually we start it with 0. So j can be 0, 1, 2, 3, etc., right? And so an example, right, is um, if you ask a group of people, in this case I've got 10 people that we're asking, how many pets do you have? Right? And I know this is sort of an elementary school example, but it's a really good exercise that will help you get familiar with the concepts, right? So J is going to be the number of pets, right? And then we'll define what is called n of j. And n of j is literally the number of people that responded with j, right? So, for example, if our data looked something like this, where we had, right, say the maximum number of pets that people responded with is that they had 3 pets. So we start with, 2 people said they have 0 pets, okay? 2 people said they have 1 pet. 4 people say they have 2 pets, and 2 people said they have 3 pets. So we asked 10 people, right? And I did this to make our numbers easier. N of j, right, is then the number of people that responded with j, right? So now we can define what we'll call capital N. And capital N is the total number of responses, right? And so obviously this would be, in this case it would be 10, right? But we can write this out mathematically, that n is equal to the sum from j equals 0 to infinity, right? From j equals 0 to infinity, right? Even though we're only going up to 3, theoretically we could get 4, 5, 6, 7. Somebody might have 375 pets, right? We could go up to however many we want. So we're just going to sum in general from j equals 0, right, our smallest amount, to whatever, of n of j, right? And we'll note that, right, what is n of 4? Well, how many people responded with 4 pets? 0, right? So everything else is going to be 0. And all this means, hopefully you understand the sigma notation, is we're going to start with 0. N of 0 is 2, right? Then we're going to go up to 1, right? And then for each term, we're going to add them together. So it's n of 0 plus n of 1 plus n of 2 plus n of 3 plus n of 4 plus n of 5. And if we do all that, we'll get, in this case, we'll get 10, right? So now I'm going to define something else, which hopefully you are familiar with. I'm going to erase this. Hopefully you'll figure out what capital N means, right? And now I'm going to look at probability, P. Ooh, I just want to have a new color for this. Go on blue. So P of J. P is the probability of, if I picked a response at random, getting J. And probability is just a ratio. It's the ratio, and this, again, you should be familiar with this, the number of people that responded with J divided by the total number of people, right? So the P of 1, right, would be 2 divided by 10, right? N of 1, which is 2, divided by big N, which is 10, right? So P of 0 would be 0.2, P of 1 would be 0.2, P of 2 would be 0.4, P of 3 would be 0.2, right? And then we can define the average, right? But in fact, in quantum mechanics, we're going to call the average something a little bit different, which is a bit of a misnomer. So the average, we're going to call the expectation value. And you'll see why that's not a really great name, right? Expectation value means sort of if I pick one at random, this is what I should expect to get, but that's not actually what it means. So I'll show you. So the expectation, which is going to have these triangle brackets, the expectation value of j, the expectation value of j is equal to, right, I'm going to have the sum from j equals 0 to infinity of j times n sub j over capital N, right? And it turns out that this is equal to the sum, and now as a shorthand, I'm just going to write the sum over j, right? That just means all possible values of j times p of j, right? And we can see that. And you may not have seen the average done like this, but I'll just show you, right? J times n sub j, that's just adding up j, right? It's it's multiplication, which is repeated addition. You're adding up j the number of times for each response, right? So here you'd be adding up 0 plus 0, right? That's 0 times n of 0. Then 1 plus 1, and then 2 plus 2, 2 plus 2 plus 2, right? You're just adding up, you're just basically adding up all the results, right? And then dividing by the total number, right? This is the formula for average. And if we end up doing this, and if you do this, you'll get that for our data set, our expectation value is 1.6. And that's a little bit weird because if we choose one of our responses at random, we won't expect to get 1.6. In fact, 1.6 is not even possible. It's not an option, right? And so sometimes that will happen. The expectation value is not actually a possible value. It's just another name for the average. So I've got a few more things to do. I'm going to erase this. Hopefully you've got this down. And keep our table up. So now I want to look at functions. And if I've got some function of j, f of j, right? And I want to take the expectation value of that function, right? And hopefully if we do an example, this will make more sense to you. I'm going to fix that up a little bit. There we go. So what this is similarly, right, how if we think about it, the expectation value of j is equal to, I'll rewrite this as what we had before, the sum over all possible values of j times p of j, right? We're just going to replace this j here with f of j, right? And what it's doing is it's just, you'll see actually, I think it's probably better to just show it by example. So for sum over all possible values of j, of f of j times p of j. Right? And what this is just the average value of f of j for our response, right? So in fact, if you made a table, right? If you added to this table f of j, and then just took the average of that table, right? Adding up each response, instead of taking the average of j, taking the average of f of j, you would get the same thing as that. So here's an example. Some function of j, let's go with j squared, right? So I want the expectation value of j squared, right? Which is, right, the sum over all possible values of j squared times p of j. Now, if you want to test this out, you can add to the table a column for j squared, right? And then you'll get 0, 1, 4, and 9, right? And then if you just do the normal way, 0 plus 0 plus 1 plus 1 plus 4 plus 4 plus 4 plus 4 plus 9, and then divide, again, by the total result, you'll get the average value of j squared, right? But if we can do it this way too, and you can also check that if you do it this way, you know, going from 0 to 1 to 2 to 3, doing all of this, what you'll get for the expectation value of j squared will be 3.6. And the other interesting thing is the expectation value of j squared is not right? So I'll write this out here. The expectation value of j squared is not the expectation value of j squared, right? Actually, the difference between these two values will end up being very, very important, and you will see that soon. Okay, so I'm gonna erase this right now. Hopefully you had that down. I've got 3 more things I believe that I would like to touch on in this video. So the first thing is another function, which is delta j. Delta j. And delta j is the uncertainty, or not the uncertainty, sorry, the deviation, right? Not the standard deviation, we'll talk about that in a minute, but this is just the deviation. The amount that j differs from the average, right? So j minus the expectation value of j, right? And we can figure out what the expectation value of this quantity is too. Now, it just so happens that based on the way averages are defined, it ends up being that this will always be equal to 0, and you can check that out yourself, right? For example, right? So I'll do this here. This would be the sum over all possible values of j of delta j times p of j. And if you do this out, right, this would be, well, let's start with j equals 0. So delta j would be 1.6, because that's 1.6 away from our average of 1.6, times the probability. So it would be 1.6 times 0.2. 1.6 times 0.2. Then if we go to 1, it would be, delta j would be 0.6, so 0.6 times 0.2. And then minus, right, because our next delta j is going to be negative 0.4, right? Because it's 2, it would be, here we'd have 2 minus 1.6. Oh, sorry. Hopefully you caught me on this. I actually did it the other way around. I did the expectation value minus the value of j. So actually it would be negative 1.6 times 0.2. Then it would be minus 0.6 times 0.2. Then it would be plus. Sorry. Hopefully you caught that. Then it would be plus 0.4 times. It would be plus 0.4 times. That's our delta j, and our probability is 0.4, so plus 0.4 times 0.4, and then delta j for 3 would be 1.4, so plus 1.4 times 0.2. I believe I did that right, but anyways, if you add that all up, you'll end up getting 0, right? And that kind of makes sense, that that the average should be the spot where any value, right, where the deviation from the average is expected to be is on average 0, if that makes sense. But that's the way the average is defined, right? However, there is something that could be important, right? Because notice, right, the average is actually, this is probably the best way to explain it. The average is set up so that the deviation on the lower side and the deviation on the upper side are the same. Right? So if you take this, right, it will be 0 because the negative and positive parts will cancel out. But what if you take the expectation value instead of the deviation? Take the expectation value of the deviation squared, right? Right? Well, this case, you can actually do that, right? And I can let you go and figure that out on your own, what the value of the deviation or what the expectation value of the deviation squared is. Um, but I can tell you that you're going to get, if I did this right, 1.04. 1.04. And I'll show you another way we can actually get to that. And now this we're going to call our standard deviation squared, right? And so if we square root it, then we'll get, the square root of 1.04 will be the standard deviation. Standard deviation is a measure of uncertainty. And that should make sense, right? Because the more the values, right, deviate, the square is just a way to, make that number positive, right? And then we just square root it. Um, if we, and we'll see that the standard deviation actually in quantum mechanics will be very useful. But the more, right, delta J, if delta J is higher, either positive or negative, more positive or more negative, its square will be higher, right? And uncertainty is greater when the data deviates from the average more. If the data deviates from the average very little, uncertainty is going to be really small. The standard deviation would then be really small. If this delta J is either really positive or really negative, meaning the data is all spread out all over the place, the standard deviation will be pretty high because the expectation of delta J squared will be high. Um, and so that should give you an intuition of why this is uncertainty. But it turns out, and I'm not going to prove this, but it actually turns out that sigma squared is equal to um, J squared, or sorry, the expectation value of J squared minus the expectation value of J, that squared. And if you do this, you'll get 1.04. So that's pretty cool that it turns out the same the both ways. And this is really important. So hopefully you're kind of absorbing this. I've got one other generalization that I want to make before I end this video, which is what if we asked a question where the answer wasn't necessarily an integer? It wasn't necessarily 0, 1, 2, or 3. Right? We can still do this thing with j still being an integer, but instead, right, we would not be collecting the value of j. Right? Would be what we call our dummy variable. It's our counting variable. It would mean that, right, response number 0, right, say we're, asking for like GPA, right? And say we get the responses of 4.0, 3.75, and 2.9. These are just random numbers, just to have 3 to just keep it simple, right? Well, this might be labeled our j equals 0 response. This would be our j equals 1 response. This would be our j equals 2 response. And this we would call our a sub j, right? So a sub 0 would be 4.0, a sub 1 would be 3.75, a sub j would just mean the jth response, right? And so j would just be our counting variable, right? We would just have to account for j equals 0, 1, 2, 3, all of the possible responses that we'd get, right? All the possible a sub j's would be if we, count all the possible j's. Hopefully that makes sense, right? You label each of the responses and you just count them up. So you add the everything that has to do with j equals 0, right? And then it wouldn't really make sense because j is just a dummy variable. We wouldn't want the average value of j. We just want the average value of a sub j, right? And the average value of a sub j, we just plug it into the formula, right, where we'd sum up, right? Could probably erase this, but I'm gonna just, the expectation value of a sub j would be on the sum over all possible values of j, of a sub j times p of j, right? It's saying a sub j is the response, right, is the jth response, and p sub j is the probability of the jth response, right? And then we can do functions of a sub j, so we could look at the expectation value of a sub j squared, right? Hopefully this makes sense. We'd just be using j as a counter, and everything else, right, it would just be like saying that we're just adding up for each possible response, the response times the probability of that response, right? So hopefully that makes sense. It's just a way of still being able to use this because for the sigma notation, j has to be an integer. So it's just a way of just counting the responses. Again, hopefully that makes sense. If it doesn't, just rewatch this a few times. It's probably the best way to explain it. It's just j is just our dummy variable. It is a counting variable, right? Um, and if you need to, maybe try to create a table for this and try to see if how this works and look at, the standard deviation, just make up some numbers and see how this all works. Okay, I will see you in the next video.